Hi, and welcome to our presentation on accelerating time to design closure and silicon success for advanced process node SoCs. My name is Wei Li Tan. I'm a product manager for the Solido Characterization Suite at Siemens EDA, and I'm joined today by Henry Chang, Senior Director of Product Management for the Aprisa Group at Siemens EDA. We'll start with a recap of the main challenges on design closure at advanced process nodes and cover the digital methodology requirements for this category of designs and how they're addressed. After that, we'll describe how Aprisa Digital Implementation and Solido Characterization Suite address these challenges, along with results and example case studies of applying these methods in production flows, followed by a summary and wrap-up. Let's start with advanced node design challenges. Digital implementation has evolved throughout the past couple of decades, from 65 nanometer process technology to the latest cutting-edge 5 nanometer and smaller nodes. Due to silicon manufacturing limits, smaller transistor and interconnect feature sizes, and designs becoming more complex in general, several challenges have emerged for digital implementation teams. One of these challenges is pre-route to post-route correlation. As process technology shrinks, wire widths become extremely thin, especially for multi-patterning metal layers. Because of this, resistivity has become the main contributor to timing in traditional flows. This introduces a larger number of iterations needed for design closure and extra margins padded at the pre-route stage, which generally causes over-design and ultimately suboptimal power, performance, and area in the final design. Another design challenge is that the number of process, voltage, and temperature corners, or PVT corners for short, have increased drastically. Coupled with additional sign-off timing modes, this results in more than 100 multi-corner multi-mode or MCMM scenarios that have to be evaluated during sign-off. In addition, the effects of on-chip variation, or OCV, have become a major factor in timing and power and may even exceed the impact of regular timing and power data in nominal liberty timing models. We'll go through each of these in more detail in the next few slides. Let's talk about pre- to post-route correlation first. The semiconductor industry has seen a few paradigm shifts over the years, one of them being the basic considerations for place and route. The first generation place and route was simply the placement and routing of all instances in the design. Interconnect delay was negligible, and design timing was mainly dominated by gate delay. So if your design met timing in synthesis, you could throw it over the wall to the place and route team, and the design would meet final timing without requiring a lot of timing-driven features. This was using what we call a gate-centric flow. That simplicity changed around 180 nanometers when interconnect capacitance started to be a dominant factor of total timing path delay. Here, path timing became dependent on cell placement. This created the need for more timing-driven placement solutions called placement-centric flows. The timing-driven placement had to converge before you could hand it off for routing, but in most cases, the final timing was met without the specific need for accurate prediction of the detailed routing topology. The most recent shift is when moving to 16 nanometer and smaller process nodes. Because of shrinking line widths, particularly in multi-patterning layers, resistance has become more dominant than capacitance in the total path delay, and wire resistance depends on not only the length and width of the wires, but also on the detailed routing topology such as routing layers, vias, and routing patterns, all of which needs to be understood in the placement stage in order to accurately predict the timing of your design. This forms the basis of the detailed routing centric approach that we will describe in more detail in the latter section of this presentation. To visualize how traditional placement-centric approaches suffer severe correlation problems between the pre-route timing estimation and actual post-route timing, we use the correlation plots shown. Here, perfect correlation would be a single line at a 45-degree angle, while differences in pre- and post-route timing are noted as points that diverge from that 45-degree middle line. At 65 nanometer, the pre-route Steiner delays versus final routed delays are mostly correlated. At 28 nanometers, the correlation starts to diverge a bit, but is still generally acceptable. And at 16 nanometers, it gets quite bad and can severely impact timing closure and power performance in the area of the final design. Finally, at 7 nanometers, we have an almost random plot where the predicted delay in the pre-route stage almost has no bearing on the post-route delays. To summarize this point, at advanced process nodes, placement engines cannot produce convergent results without information of detailed routing topology today, which is a shift in the basic factors being considered by traditional place and route tools that assume detailed routing only comes after placement and placement-based optimization. The second challenge we mentioned was the explosion in number of multi-corner multimode scenarios, or MCMM scenarios for short. The number of scenarios in MCMM timing and optimization are based on number of process, voltage, and temperature, or PVT corners, as well as the number of design modes that all need to pass static timing analysis. The biggest culprit behind this rapid increase is the large number of PVT corners needed for sign-off STA. Today, at 7 nanometers, having 50 to 100 PVT corners used at sign-off is quite common. This is compared to only a handful of PVT corners required at 65 or even 40 nanometer designs. There's no longer a best case or worst case corner, so many corners in between have to all be timing validated. Due to the same reasons, optimization at the implementation stage and especially ECO changes have to be internally timed for a large number of MCMM scenarios so that the end result can match with final sign-off STA. In addition, as the number of PVTs grow, we run into an increasingly common issue where the Liberty models for the specific PVTs needed for sign-off STA or MCMM optimization is not readily available. In this case, the design team is left with two rather unappealing choices of either trying to characterize a new PVT from scratch with limited characterization information of the rest of the corners, or applying derates or interpolation to mimic the timing behavior of the uncharacterized PVT corners. Here we'll illustrate why characterizing missing PVTs is such a challenge. Aside from requiring SpiceNet lists and Foundry PDKs that sometimes are not readily available to digital teams, there is also a significant amount of setup to run a current factor in nonlinear behavior within table data or across PVTs. Without a reliable way to obtain .libs at the required PVTs, any kind of multimode, multi-corner STA will run into problems, and design teams end up with incorrect timing, power, or noise calculated by STA. This leads to overdesign and schedule delays, or in severe cases, silicon failure. The third design challenge we will discuss today is on-chip variation. To provide some background information on this topic, Over the past decade, due to shrinking feature sizes and limits to silicon manufacturing, on-chip variation, or OCV for short, has had a growing impact on design closure. Today, 7nm and 5nm designs can see OCV effects impact timing just as much as nominal timing. At 65nm or 40nm, a flat derate factor was generally sufficient to model OCV. Using this method is very pessimistic because it attempts to capture the worst effects of OCV. However, because OCV effects at 65 or 40nm are generally very mild, this still allows the design to pass timing. As OCV effects increase in 28nm, using AOCV or advanced OCV reduces the timing pessimism by determining the cell's derate based on the number of logic stages in the shortest path, which is slightly more accurate than using a flat derate. POCV, or parametric OCV, increases the accuracy of OCV modeling by introducing a statistical mean and variance to model the variation of a cell. However, each cell is still modeled by a simple mean and variation. At 16nm, 7nm, and smaller process nodes, due to the severity of OCV effects, it's simply not feasible to take OCV into account and still meet power, performance, and area targets with these older methods. So LVF, or Liberty Variation Format, provides the granularity and per timing arc and slew law combination needed to achieve a high level of precision on the amount of OCV applied. As shown here, increasingly granular methods of modeling OCV have been introduced over the past years as a measure to counter the increasing effect of OCV on static timing analysis, with LVF being the most precise and the main method of modeling OCV for advanced process nodes today. LVF is an excellent way of modeling OCV, the ability to apply a precise amount of pessimism to individual timing arcs. How is LVF data characterized though? Well, each LVF table entry technically requires thousands of Monte Carlo simulations, which will make characterization run thousands of times slower. However, characterization tools typically have methods of reducing that to 3 to 10 times of nominal runtime, which is still a big challenge, but feasible. These runtime reduction methods may also make LVF characterized data more prone to errors and may completely invalidate your ST results if the errors are not caught. Because of that, validation of LVF information is extremely important. As mentioned earlier, the impact of LVF on timing and power can be as large as nominal timing, so it can definitely make or break a design. However, it's also very difficult to verify LVF data. Since the data is statistical in nature, what is the correct reference value to validate against? This is the question many library and design teams face. Without the proper tools, LVF data validation may take months and still not catch issues reliably. Here are a couple of examples of LVF data problems. These results are objectively incorrect since statistical timing and power properties of standard cells or other IP isn't supposed to fluctuate wildly like shown here. However, this level of noisiness in .lit data is really quite common even in production LVF.libs. In the previous section, we looked at the design challenges at advanced nodes and how the many factors may potentially introduce design breaking problems if not handled correctly. Now, let's move on to defining a digital implementation methodology that addresses these challenges. What do we need in a digital implementation methodology for it to support advanced process node designs? The first design challenge we discussed was pre to post route correlation. In order to achieve design closure that can converge from placement to post route, we need an engine that bases its placement and optimization decisions on detailed routing topology. In addition, we also need a post-route STA to match up with earlier parts of the design flow, such as synthesis and floor planning. Therefore, we also need to verify all STA inputs, including timing consistency between nonlinear delay models, or NLDM, and current source models, or CCS. Next, we also need a place and route engine that not only supports multi-corner multi-mode optimization, but is also able to handle a large number of MC/MM scenarios during optimization, and especially during ECOs. In that context, we also need a method to quickly and accurately produce .libs to cover all the additional PVTs required by optimization and sign-off, and make sure these additional PVTs are in alignment with the original set of .libs. Last but not least, we need comprehensive support for LVF all the way from full verification of the input LVF.libs to LVF support and path-based timing during optimization. Siemens provides a digital methodology which includes Solido Characterization Suite and Aprisa that is able to deliver on each of those requirements and provide a complete solution from accuracy verified inputs to a sign-off ready design database. We'll go into each of these in more detail later, but here's a summary. First, to ensure pre to post-route correlation, our approach starts with verifying that correct and precise inputs are provided to the place and route environment. Solido Characterization Suite provides comprehensive .lib verification, including NLDM and CCS consistency, and a full machine learning enabled check on all input .libs. Next, the Aprisa digital implementation solution utilizes a detailed route-centric approach that ensures that post-route correlation is built in to earlier stages in the flow. Aprisa also supports multi-corner multi-mode optimization and ECO and can read in large MCMM scenario sets to support the increasing PVTs and modes required in advanced process node designs. To support this, Solido Characterization Suite uses machine learning to produce accurate .libs at PVT corners specified by the user to supplement the original set of .libs. And finally, both Solido Characterization Suite and Aprisa fully support LVF, including moments, throughout the entire flow from .lib production and verification all the way to post-route stages. Used together, Solido Characterization Suite and Aprisa eliminate unnecessary margins to provide better quality of results while reducing time spent in design closure iterations. In the next two sections, we'll go through Solido Characterization Suite and Aprisa in more detail to explain how they deliver on the requirements for advanced process node designs. I'll start first with Solido Characterization Suite. Solido Characterization Suite is a machine learning-enabled Liberty model production and verification solution. It includes Analytics and Generator as two of its main components. Analytics is a comprehensive library verification tool, while Generator produces .libs and new PVTs. Both tools work on all types of .libs, such as standard cells, IOs, memories, even custom cells if we have .lib representation for them. The tools support all types of .lib data, such as timing, power, noise, and LVF data, including moments, which is important for advanced process node designs. Generator and Analytics are both characterizer independent, so they work with any library characterization flow today. They help design and library teams achieve better quality libraries, shorter and more predictable production schedules, and improve power, performance, and area in the final design. Solido Analytics is designed to be a lightweight, yet complete solution for .lib verification. Our users don't have to be experts in library characterization, although library teams will definitely appreciate what the tool offers. It verifies .libs using a combination of rule-based checks, machine learning outlier detection, and a full set of .lib comparison capabilities, all supported by a Liberty Visualizer GUI that allows users to quickly and effectively explore .lib contents and investigate any issues that are uncovered. Overall, Solido Analytics helps library and design teams fully verify .libs in hours instead of weeks, and also helps digital implementation teams catch .lib issues before going into production. The rule-based checks in Analytics are fast and parallelized, provide all static checks required to make sure Liberty models are structurally correct, and also includes an API to add in any new validation rules not covered by the built-in rule set. Here's an example of the library visualizer being used to show a violation found from rule-based checks. We're using the CCS versus NLDM consistency rule as an example, which is used to check whether timing properties derived from CCS tables and the timing properties from NLDM lookup tables match each other. This is a check that's especially useful to ensure post-route